Hello everybody, and welcome to my 15th video. This is on base n DeMorgan's theorem. I'm going to be going through 3 examples, one in the binary case, one in the ternary case, and one in the quaternary case. Obviously base n is 2, 3 and 4. So we're going to start off by talking about unary and binary operators. For a unary operator, it's called unary because there's only one input, and a binary operator is called a binary operator because it has 2 inputs or more. Now, this is a frequency table for the output of a binary operator and unary operator. So here we have FNM, F for frequency, N is the number of inputs, and M is the mode. And we can see that FNM here is m to the n minus m minus 1 to the n, where m is the mode, this is m here, n is the number of inputs, and n, capital N, is the base. So m is between n and 1, where n is the base. Now, for example, in the Boolean system, for an AND gate, there are 3 zeros and 1 1. For an OR gate, there are 3 ones and 1 0. So this table denotes the frequency of the logic state and the output of any binary operator. For example, the binary ternary maximum of function for 3 inputs has 19 2s, 7 1s and 1 0. For a quaternary function of 4 inputs, say the minimum of the quaternary minimum of function has 175 zeros, 65 1s, 15 2s and 1 3. So for a binary operator, each logic state in the base must have a unique frequency. So basically, for every value of m, there is a different logic state assigned to a frequency. For a union operator, this applies, but the frequency is always 1 for each logic state. So the number of unary or binary operators is n factorial. For example, in the Boolean system, there are 2 unary operators, A and not A, and 2 binary operators, and or. Right. So we're going to talk about a method for determining the output of a binary operator. So this is the binary minimum of function. This is the frequency and logic state shown in the table previously. So the minimum of function has 5 zeros, 3 1s and 1 2. So you take step 1, you look for the frequency, logic state with the maximum frequency, the greatest frequency, in this case it's 5, and you look for it on the inputs of any of the inputs, look for a 0 on any of the inputs, and write the output logic state there, which in this case is a 0. And step 2, for the remaining outputs of the truth table, you take the next most frequent number, which is a 3, which has a logic state of a 1, and you look for those on the inputs, and you fill the output, fill that logic state on the output. And step 3, you look for the least frequent number, which is in this case has a frequency of 1 and logic state 2, and you look for it on the input and you fill that in on the output. So this method works for any function. All you need is the frequency table, and you work in ascending order of logic states with the frequency, and you fill them in the order that they are presented. So this is the minimum of function. You can see the output there is equal to min b. So here we have an example of DeMorgan's theorem drawn in function form with circuit diagram form, sorry. So I have not x equals n minus 1 minus x plus is x plus 1 modulo n, and x minus is x plus n minus 1 modulo n. In the binary case, all these functions are equal to not x. These are not functions. So if you have minimum function in the binary form, in the Boolean form, is the AND function, the maximum is the OR function. So not x is the not function. So here we have the minimum function, and that's the equivalent to not A, max not B, knotted, with the output complemented, knotted. So if this is equivalent to that, if there's any complementation present on the input of the minimum function before you apply DeMorgan's theorem, then this has to be substituted into here from there. So any complementation present on the input of the minimum function has to be complemented after the complementation present on the input and before the complementation present on the output. So there's an order to it. If this was a ternary case, then x plus and then not x wouldn't be the same as not x, x plus. So the order you do the things, do the complementation in matters. And then on the output, not x and x minus is not the same as x minus, then followed by not x. So basically, any complementation for the input, the complementation due to DeMorgan's theorem goes after the complementation on the inputs and before complementation on the output. So this is the binary case, Boolean case. Here we have the AND function and the OR function, A and not A. And we're going to use this notation here. A to the U is some function of A, B to the V is some function of B, F1 and F2 are the binary operators, in this case AND and OR. And W is some function of the output. AX is some function of A, BY is some function of B, and Z is some function of the output of F2. So we're going to show that not A and B knotted, not A NAND B, is equal to A or B not. So we look at the frequency tables for AND and OR. The AND has 3 zeros and 1 1. The OR has 3 1s and 1 0. And we match up the logic states and perform a mapping between the logic states. So here we have the mapping M1, M for mapping, M1. So we take the output from the AND to the OR function. So 0 goes to 1 and 1 goes to 0. So AU is AU is not A. So we take the mapping M1 here. 1 goes to 0, 0 goes to 1. BV is B, so M1 goes from 0 to a 1 to 1 to a 0 to give BY with as not B. For the output, we reverse the mapping from AND to OR to OR to AND. so it's the inverse mapping if you like. This is M2 and it's the same, a 1 to a 0 and 0 to a 1. And we look at the output W. This is for the output of the AND function, and the mapping M3 goes from a 0 to a 1 and a 1 to a 0. For the output Z of F2, we first apply mapping M2 and then M3. So a 0 goes to a 1, a 1 goes to a 0, and a 1 goes to a 0, and a 0 goes to a 1 here. So the output of the OR function has no complementation on it. So here we have the truth tables. So AU is not A, BV is B, AU and BV is not A and B, AU and BV to the W is not A and B. So that's the complement of this. And here we have the F2 function 2. AX is A, BY is not B. AX or BY is A or B not. And AX or BY to Z, there's no computation for Z. So it's the same, it's A plus B not. So you can see these two functions are the same. It's a very complicated method of doing it for the Boolean system, but it's just to show that it works for the Boolean system as well as any other base. So here we have a ternary example. The zero function and the 1 function here, listed here. The 0 function is a minimum function. The 1 function is listed in my functions videos on a ternary algebra with 6 binary operators. Video 14, I think. There are 6 such binary operators. These are ternary functions. And I'm going to show you how to do DeMorgan's theorem for these two functions. Here we have 6 union operators: A plus, A minus, A squared, A plus 2 and A minus 2. They all perform this operation. They've all got a frequency of 1. Each logic state has a frequency of 1. So we're going to use the function, this formula again as in the binary case. AU F1 BV to the W equals AX F2 BY to the Z. So A to the U is A squared, which is this one here. B plus is this function here. A minus 2 is this function here. A plus 2 is this function here. B minus is that function there, and squared is that function there. So we know, if we know the value of AU, F1, F2, BV and W, we can work out what AX, BY and Z is. So here we have the frequency tables for a 0 function and the 1 function. The 0 function has 5 zeros, 3 ones and 1 2. The 1 function has 5 ones, 3 twos and 1 0. Right. Now we take the mappings from the respective logic states of the same frequency, from the 0 to the 1. This is M1, mapping M1. So a 0 goes to a 1 goes to a 2 and a 2 goes to a 0. So we'll look at AU, which was A squared, so we just write in the function there, and we perform mapping M1 on this function to give AX. So 0 goes to a 1, 2 goes to 0, 1 goes to a 2. For variable B, BV equals B plus, so that's there. and perform mapping M1 here. So 1 goes to 2, 2 goes to 0, and 0 goes to 1. That gives by, which is B minus. Yeah, B minus. For the output, we reverse the mapping. So M2 is the inverse of M1. It's from a 1 function to a 0 function. So a 1 to a 0, a 2 to a 1, and a 0 to a 2. The output W of function F1, and we perform the output was minus 2, which is 2, 1, 0. So M3 is a 0 goes to a 2, a 1 goes to a 1, and a 2 goes to a 0. So for the output Z of function F2, which is the 1 function, a 0 goes to a 2, we'll perform mapping M2, 0 goes to a 2, 1 to a 0, a 2 to a 1, and then we perform mapping M3, this mapping here. So a 2 goes to a 0, a 0 goes to a 2, and a 1 goes to a 1. So I can see that output Z is A squared. So that's the output and that's the function. Here you have the truth table. You have A squared and A B plus, sorry. This is function F1, AU 0 BV. In this case AU is A squared and BV is B plus. Here we have the output, the same function with the output W, which is A minus 2. So we have A squared 0 B plus to the minus 2, which takes a 0 to a 2, 1 to a 1, and 2 to 0. And here we have function F2, AX equals A plus 2, BY equals B minus, AX1 BY is A plus 2, 1 B minus, and the output Z is to the squared function, so AX1 BY to the Z is A plus 2, 1 B minus squared. So the squared takes a 1 to 2, 2 to a 1, and a 0 to a 0. You can see that these two columns here, A00 BV to the W equals AX1 BY to the Z. Next we're going to look at a quaternary system. Here I have inputs A and B, the maximum, minimum and the maximum of functions. And we're going to use 6 unary operators, each with one frequency of 1. Each logic state has a frequency of 1 in the output of the function. So we have A plus plus, and A minus, A6, A plus 6, and A minus 6. So we're going to use the formula AU F1 BV to the W equals AX F2 BY to the Z. So we're going to use F1 is the minimal function, F2 is the maximal function, AU is A minus, BV is B, W is B output plus plus, and we're going to work out AX, BY and Z, output to Z. So we know F2, so we know AU, F1, BV, W and F2. I'm going to work out AX, BY and Z. So we're going to show that A minus and B plus plus equals A6 or max B minus 6 plus 6. Here we have the frequency tables for the minimum and maximum functions for the quaternary system. Here the minimum function has 7 zeros, 5 ones, 3 twos and 1 3. The maximum function has 7 threes, 5 twos, 3 ones and 1 0. This is for a 2-input function, of course. So we're going to start off with inputs, use mapping M1. So we match up the respective logic states with the same frequency and perform the mapping M1 from one logic state to another. So 0 to a 3, a 1 to a 2, a 2 to a 1, and 3 to a 0. And perform this mapping on AU, which is A minus. This is A minus. Perform the mapping there, 3 to a 0, 0 to a 3, 1 to a 2, 2 to a 1. For B, BV equals B, so perform the same mapping M1, 0 to 3, 1 to 2, 2 to 1, 3 to 0. That gives BY, which is B minus 6. Now for the output, we'll do the inverse mapping, so it's from the maximum function to the minimum function. So 3 to a 0, 1 to a 2, 2 to a 1, sorry, 1 to a 2, and a 0 to a 3, 0 to a 3. So this is mapping M2. We'll form that on the output of the minimum function. So 0 to a 2, 1 to a 3, 2 to a 0, and 3 to a 1. That's mapping M3, that's W, which is the plus plus function, A plus 2 modulo 3. Next we take the output. We take the two mappings M2 and M3 and we map M2 to the output and then take that output and apply mapping M3 to give the output Z. So M2 gives a 0 to a 3, a 1 to a 2, a 2 to a 1, a 3 to a 0, and M3 gives a 3 to a 1, a 2 to a 0, a 1 to a 3, and a 0 to a 2. So that output is A plus 6. Yeah, A plus 6. So from looking at the truth table, AU is A minus, BV is B, A minus and B there, A minus and B plus plus there. So here for the this is for function F1, function F2, AX is A6 here, BY is A minus, that should be B minus 6 there, A6 plus B minus 6 there for the OR function, for the maximum function, sorry, and this column is the output of this to the power with the plus 6 operator on the output. So 3 goes to 2, 2 goes to 3, 3 goes to 2, 2 goes to 3, 1 goes to 0, and a 0 goes to 1. Right, I think that concludes the presentation. I hope you've enjoyed it. Thanks for watching. Bye.